Okay, let's start. Hello, welcome back. So according to the schedule, this week we're going to study digital signal processing, which is a wonderful field. But I thought before going into that, let's do a couple more examples about these change of bases stuff, because this is more important. At least for our purposes, signal processing is somewhat of an application that is still important, but this is more fundamental, so I wanted to spend more time on this. So recall this universal diagram. I have two vector spaces of finite dimension, V and W. V has n dimensions, W has m dimensions. And that means that V has a basis consisting of n vectors, beta 1 to beta n. That's the basis that I chose. And likewise, W has a basis consisting of m elements. And we had this universal diagram. I told you that no matter what, so as long as the issue is about like taking transformations, turning them into matrices, or changing bases, whatever, it's always, at the end of the day, this diagram. You don't need to memorize anything but this. As long as you can put the correct terms into the correct spots, it's going to tell you what you should compute. And so I can draw it like this, or I can write it like so as well. So this symbol is a symbol for composition. I'm saying that this, so if I take a column matrix, multiplying this column matrix, or column vector if you want, from the left by this representing matrix is the same thing as taking this column matrix, applying m sub beta, the linear chart given by the basis beta, inverse, so that I go back to the vector space. Then I apply my transformation, and then I apply my chart again. Okay, so this just means that the composition of transformations. Let me add one more notation. And this is going to be the analog of the identity matrix as a transformation. And I'm just going to call it the identity transformation. And so I'm just going to write it id v to v. Some people write id sub v to represent that this is the identity transformation of this vector space. This is just the identity transformation. And of course, defined by identity of v for any vector equals v. Doesn't do anything. Okay, so now we have a separation. Two classes of linear transformations. This is very important in computer science, computer graphics, physics, a lot of different areas. One is called an active transformation. The other one is called a passive transformation. Okay? And throughout this class, we were so far, I think, discussing active transformations. So when we said linear transformation, we really meant active. Another way for this is alibi changing. So this is actually doing something in your space. Okay? So these are when, in the universal diagram, T is not identity. Okay? It's that simple. Then in your space, right, so the top row, I guess I should write it like this. V to V, but it's not the identity. It's a different transformation. Things move, okay? There is some motion here. Saying that my transformation is not the identity, I mean something like this is my mysterious vector space. It has a bunch of vectors in it, and they move when I apply T to it. Okay? What is more important for us in the context of changing the basis is what is called passive transformations. So these are when t is equal to identity. Okay? Now what might happen is that you may use different bases here. Okay? So in a sense, nothing is really happening in your vector space, but still numbers are changing. So you're changing the basis, for instance. And so this is, instead of active or alibi changing, so things are happening, now it's only the alias that is changing. Okay? Nothing moves, but their names change. So here's an example for this. So let's consider these two bases. So I have a certain two-dimensional vector space, okay? You can think of it as R2, but you don't need to. So I have beta, which has two vectors, and I have gamma. It too has two vectors. For some vector space, both of these are linearly independent. And so they constitute the basis. So consequently, V has dimension 2. Right? Because by definition, the dimension of a vector space is the number of vectors in a basis. And we said that, one vector space might have many bases, but the number of vectors in the basis, in any basis, is going to be the same. In this case, it's 2. And so let's say that we have these relations. I'm not telling you what these vectors are, but I'm telling you that they have certain linear relationships between them. And then we have one final vector. Let me say it like this. Let's say that I am given that I have a certain vector v in my vector space whose matrix, according to the basis beta, is 3, 1. Okay? Now the question is, what is the matrix of the same vector according to the other basis? Okay, that's the question. Okay. So now, any questions so far about this? So now, let's just use the universal diagram. My vector space is V. So you see, now nothing is changing, so I'm going to use this passive perspective. I'm going to say, okay, so up there I have this identity transformation. The vector doesn't change. But here I have the chart given by beta, and here I have the chart given by gamma. And so there is going to be a matrix here, according to the universal diagram. Okay. So what do we do? You plug in certain terms into this diagram and you chase it. Okay. So if you start here, starting with this, you can go back and move things around. So if I start here, going up now means applying m beta inverse. So that is to say, finding v. So the inverse of this is 3 times beta 1 plus 1 times beta 2. That's literally the definition. Right? Because m sub beta, this chart, tells you this. Take any vector, in this case it's a specific vector, but take any vector, write it as a linear combination of the basis elements, and take those coefficients and put them in the appropriate order. Okay, that's what it says. So its inverse is doing the opposite, doing the reverse. It takes a matrix and writes it as this linear combination. Now, if I were to apply my identity transformation, nothing happens to it. Okay. But now, you see, if I want to use this, instead of using betas as my vectors over which I'm taking the linear combination, I should be rewriting everything in terms of gammas. And when I do that, I'm going to get something. So when I write it in terms of gammas, I get this. 3 times, right, 4 gamma 1 plus gamma 2 plus 1 times minus 6 gamma 1 plus gamma 2. In total, this is 12 minus 6, 6 gamma 1, and then 3 plus 1 plus 4 gamma 2. So using this chart now gives me this new matrix. Okay? So this is a passive transformation, okay? Nothing is happening. It's the identity transformation. But somehow I'm getting different matrices for the same vector. The point is that I change the basis, of course. I'm changing my perspective as to how things look. And now I want to figure out, we did figure it out. There you go, here. So this right here is this. Okay? I started here, went up here. Identity transformation doesn't do anything. Rewrite everything in terms of gammas and gamma 1 and gamma 2. Use your new coordinate chart. That gives you the new representation. Same vector, different matrices. Okay? So only the alias changed, as you see. It's the same vector. It's the vector v, this particular vector. I was given a certain name for it with respect to, or a certain matrix representation with respect to a certain basis, and I changed ultimately the basis, and again obtained a new matrix for my vector.
Where did you get the rewrite of beta?
Oh, these were given to me. Okay. Yeah. If they hadn't given this to me, I wouldn't be able to do this. Any other questions?
So you could, so I guess the next step, if you wanted to, would be to get the matrix.
Yes.
That would go from.
Exactly.
Yeah.
Yes. But before going into that, is this sort of motion clear? Write everything on the universal diagram and read out the terms, essentially. Follow the flow chart, and it's going to tell you. So this is the reason why I'm calling this universal is that if you don't know something about this, you can, and if you know the rest, you can still complete it and so on. That's sort of the universality that I'm referring to here. And like your colleague said, the next step is to figure out how to take any vector whatsoever and relate the matrix representation of that vector with respect to the first basis to the second basis. Okay? So that is to say, finding this change of basis matrix. Or in other words, the associated passive transformation, the associated alias changing transformation in general. So let's try to find this out. So here, what we have is this. According to the universal diagram that I wrote over here, T is identity. I have beta and gamma, and I told you that this going this way should be the same thing as left multiplication by this matrix. So this is a matrix such that when I multiply any 2 by 1 matrix by it, I get another 2 by 1. And in particular, if I were to start with 3, 1 over there, I get 6, 4. In any event, this is 2 by 1, this is 2 by 1. Based on dimensional analysis, we know that this should be 2 by 2. Okay? So I have 4 numbers to figure out. I'm trying to figure out what this change of basis matrix is. Okay, so let me write it here. Gamma to beta of identity is the change of basis matrix transformation let's say like this, that transforms beta matrices, so matrix representations with respect to beta, to gamma matrices. Okay, so plugging this back into this, I have this ABCD times 3, 1 equals 6, 4. So I have 4 unknowns, but I have 2 equations. This is not quite solvable yet. I want to get unique numbers here. I want to get a unique A, unique B, unique C, and unique D. But what you can do is this. You can use more general vectors, because we know from matrix algebra that AC is nothing but ABCD applied to 1, 0. And similarly, BD is equal to ABCD multiplied by 0, 1. Now, in the universal diagram, note that these left multiplication corresponds to this bottom arrow. So 1, 0 and 0, 1 are here. So I can then chase this diagram again using 1, 0 and 0, 1. At the bottom left corner, if I were to start with 1, 0. Right, so if I start with 1, 0, I end up with AC over here, according to what I wrote there. Now, do you have any ideas as to what this should be?
Could it just be V to V?
Say again?
Could it be V identity to V identity?
Oh, yeah, yeah. So, yes, yes, that is true. This is identity, but I want an element, right? So this is a vector in this matrix space. I want a vector in V. What does that be?
If it looks like the one on top, shouldn't it just be like 1A plus 0C?
I'm
kind of referencing like above.
That's true, but you're going this way. I want to go this way. I want to use M beta.
So is it just 1 beta m plus 0?
Yeah, exactly. It's just beta 1. Right? I think that's what you meant.
Yeah.
Yeah. Right? So because M sub beta takes any vector whatsoever and gives you back its matrix representation with respect to beta. What is the matrix representation of beta 1, which is a valid vector, with respect to beta? It's just going to be 1, 0. Okay, because beta 1 is 1 times beta 1 plus 0 times beta 2. In any event, once you have this, we know that beta 1, it is given to us, is equal to 4 gamma 1 plus gamma 2. But then going down, this gives us that this matrix is 4, 1. Okay? I hope I'm not making a mistake. Let me think. Okay. I think it's the problem. It is correct. So this is the first part. You see, we discovered the first column of this change of basis matrix. But I can apply the same thing to 0, 1. Of course, in linear charts, 0, 1 is nothing but beta 2, according to this linear chart, m sub beta. And this, under identity, goes to minus 6 gamma 1 plus gamma 2. It's the same thing, of course. It's equal to beta 2. And then with respect to gamma charts, this gives me minus 6, 1. And again, this gives me BD. So BD has to be equal to minus 6, 1. And ultimately, this tells us that this change of basis matrix from beta to gamma is nothing but 4, 1 minus 6, 1. Let me write it here. Of course, note that immediately computing the determinant, it's a non-zero number, so it is invertible. This is important. Change of basis matrices are always invertible. Is a change of the transform. It's always invertible. Okay? Any change of basis matrix is invertible. What could the inverse be of this?
Going from sigma to beta.
Exactly, yeah. So if this guy is changing from beta to gamma, its inverse should be the other way around. So So let me leave that to you as an exercise then. What is the change of basis matrix from gamma to beta? Right? All you need to do is to invert this matrix. Let me just write it here. Compute the change of basis matrix. Let me just say what did I, okay. Gamma to beta. Okay. Any questions about this example?
So when you give like the beta of 1 equals 4 gamma of 1 plus gamma 2, for those two equations, how come that isn't the inverse? Like if I fed the vector like gamma of 1 and beta of 1 into the matrix 4, 1, negative 6, 1, how come, like I feel like intuitively that feels like it should be the inverse.
I see. Well, think of it this way. You cannot feed really gamma 1 and gamma 2 into this matrix that we found from the left. I mean, you can. It would compute two things, but it wouldn't correspond to this identity transformation. You would be messing up something else in the universal diagram. Yeah. So that's the difference. The really confusing thing here is that the semantics, so the syntax is always going to be okay most of the time. It's like you can just compute things. But what you compute is not going to be what you actually wanted to compute. So the semantics, so this diagram, this universal diagram, keeps track of the semantics as well. That's sort of like the benefit of this. Otherwise, like you can take whatever, this matrix multiplied by some other column matrix and so on, it would compute you things. You can just like, it would make sense. It would be syntactic. But not necessarily would it correspond to what you wanted to compute. So, any other, yes?
So to do this, we need to have what B1 and B2 equals as well as the 3-1 piece.
Ask again.
So like this left side of the board, we need to have that information so that we can figure out what.
Yeah, let me just say it this way. As long as you have sufficiently many information here, like let's say 3 of the corners are known and the arrows are known, so they're asking you the 4th one, you would be able to answer it. Or maybe you know partial information about this, and so on, but ultimately it's like Sudoku, and you can just fill everything out. Yeah, exactly. So the point is that there's always, insofar as it's a solvable question that you're encountering, there's always a unique way to fill this universal diagram. Yeah, this is very useful. I highly recommend that you get accustomed to using this. Any other questions? Okay, let's do another example. Probably you're going to see problems like this in problem set 7, and also possibly in the midterm. So we're not wearing the straight jackets anymore, so I can just think of vectors in R2 or Rn as matrices. The point is that underneath everything, underneath all these interpretations, now we know that there's some basis and so on. It's always with respect to a basis in everything. So let's look at this. I'm going to change letters because that's what they use in this book for now. So B1 is going to be -9, 1. B2 is -5, -1. And capital B, curly B, is B1, B2. Okay, C1 is 1 minus 4, and C2 is 3 minus 5. And again, let me use curly C as an abbreviation for C1 and C2. Okay. So I can just imagine these to be now vectors in R2, or if you feel more comfortable with that, you can just consider, you can just take your vector space of interest to be the space of 2x1 matrices. Nothing would change. Now first, let's verify that these are bases. How can I verify that these are bases indeed? Exactly. So how can I figure out if B1 and B2 are linearly independent?
I think that you should put them in a matrix and like try to reduce them and see that they're, like get it to like the reduced echelon form.
Yeah, and the reduced echelon form would be the identity matrix, right? If they are bases, and vice versa. If that is the case, that means that, and a possibly faster way of doing this is to put these in a matrix and look at the determinant. If the determinant is non-zero, then they're bases. So clearly this determinant is a non-zero number, so it is invertible. So this beta, so B is indeed a basis.
How can you know that it spans B1? How can you know, given B1 and B2 in like some vector space like curly B, like how can you know it spans?
Yeah, because two vectors can span at most 2 dimensions. Linear independence tells me that there's no redundancy, so they do the maximum thing. Yeah. And likewise here, looking at this -5 and then some other number that is not -5 or +5. So that means that this, so C1 and C2 are linearly independent. Consequently, this is also a basis. Okay. So now what I can do is, or what we can do is ask questions. And the questions are, what are the change of bases from B to C and C to B. Now, based on this, all I need to do is to compute one of them. The other one is just going to be the inverse matrix. So okay. So let me also remind you. So according to my notation, this would be the change of basis matrix from B to C. In the book, the way they write it is like this. P and then an arrow underneath, and then it's like this. So this is the notation in the book. This is the notation that I'm using. The notation I'm using is slightly more expressive, I would say, but you can use either one, of course. The point is that insofar as we're looking at change of basis matrices, my actual transformation is going to be identity. So it's going to be a passive transformation. Vectors are not going to move, okay? All that's going to happen is their names are going to change. Yeah, so let's start with this first one. So I guess I can write R2 here. It's going to be identity at the top. And then I have two linear charts this way. This is M sub B. This is M sub C. This goes into the space of 2 by 1 matrices. And of course, eventually, like, you may just stop writing this, right? So it just takes some time. I would suggest that know how to draw this diagram and draw it when you're getting confused about what is to be done. So I'm trying to compute this matrix here, okay? And so this is all that's given to me. Well, maybe I should ask, what should I do here? How can I proceed? So first of all, I can say, for instance, that this matrix multiplication this matrix that I'm going to multiply matrices with should be 2 by 2, right? Because it's taking 2 by 1, turns it into 2 by 1, and this is by lift multiplication. So the matrix should be 2 by 2, and it's somewhat straightforward from the idea that it should have an inverse 2, that it should be a square matrix. So I have 4 numbers to figure out. So A, B, C, D. I need 4 numbers.
Don't you want to do 1, 0 times, or I guess 1 times AC? Like you want to do the matrix algebra thing.
Yes.
Where you do the 1, 0 AC,
Mm-hmm.
0, 1 BD, and you go up from the bottom left corner.
Yes.
And then you do the identity, and then you go down, and that's what you want to do.
Yes. Ultimately, that's true. So this is the idea. This is what your colleague suggested. So if I start with 1, 0 at the top left corner, above it becomes B1. And identity, when I apply identity, it's still B1. But you see now, to use this new coordinate chart, I need to write B1 as a linear combination of C1 and C2. Okay, B1 is a legitimate vector. I can try splitting it using the other basis. And so that's what I'm going to do. And in fact, before even doing this, let me just do this. If I were to take A, B, C, D and multiply this from the left by it, I have another term here, which is AC. So this tells me then that B1 equals A times C1 plus C times C1. So maybe I should use a different letter then. Greek letters get into here then. Alpha, beta, gamma, and delta. This is alpha and gamma. This is alpha. This is gamma. Okay, so this gives us one equation, okay? B1, two numbers, equals unknown alpha times C1, two numbers, plus unknown gamma times C2. Two more numbers. So this gives you two equations with two unknowns. Applying the same thing to this, so if I start with 0, 1 instead, filling the diagram, I get this. B2 up top. If I go this way, I go to beta delta, and if I go up, I get that B2 has to be beta C1 plus delta C2. Okay. So you see now we have four equations with four unknowns. I claim that the solutions for these two gives me everything, gives me what I want. So the first equation tells me this. Minus 9, 1 equals alpha times 1 minus 4 plus gamma times 3 minus 5. And the second equation, maybe I should box these. Gives me minus 5 minus 1 and beta and then delta here, and then this is going to be 1 minus 4 and this is going to be 3 minus 5. System of linear equations with four unknowns and four equations. I'm not going to spend time solving this at this stage, but there's multiple ways of doing this. You can do augmented matrix, however you want to do it. Ultimately, you solve it, and you get this. Four numbers. And there you go. This matrix allows you to start with a matrix representation for any vector whatsoever with respect to the B basis, and produces for you the matrix representation of the same vector. Doesn't do anything, it's a passive transformation, but it changes your perspective. Now it is giving you the same thing with respect to the C basis. Okay? And its inverse, of course, is the inverse of this matrix. Okay. Maybe I should write that as well. And we know how to invert 2 by 2 matrices now. So it's going to be again 2 by 2. 1 over the determinant, and then these two flipped, minus 3, 6 here, and then minus 4, 5. And then the determinant is minus 18 minus minus 20 is 2. So that's the inverse. Okay? If you want, you can distribute the number. Any questions about any of this? This is an important point, probably rather abstract and confusing, but It is very important, and you should know it for the midterm.
So any vector in B will be expressed by that matrix times that vector to
Yes.
a new frame.
Yes.
You're going to do this process where you use the universal diagram for each basis vector in B. Like, you do this process for B1 and B2,
Mm-hmm.
and if you had like an n-dimensional vector space, you do it.
Yes. Yeah. 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 Mm-hmm. Yeah. I mean, maybe for your for the problem that you have at hand, you don't need the full change of basis matrix. You just need a certain entry, and based on that entry, you can sort of decide to just compute a certain piece of it.
Like you're only interested in a particular vector. Like you don't need to.
Yeah. I mean, it depends on the situation. But if you want to get the whole thing, you're going to have to go through every single basis element. Yeah. 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 Any other questions? Now, the more general universal diagram supports not only passive transformations or active transformations, but it supports both of them at the same time. So it allows you to think of a situation where something is happening to your vector space or in your vector space, but at the same time, things are changing name. Okay, we can sort of factorize things. We're not going to get into that because it's not really the focus, I think, in this class. But it is really robust in terms of a linear algebraic tool, and I would highly recommend that you get accustomed to using this. And one interesting thing would be to sort of look at certain, sentences in the book that seem just like linear, that seem just like English, and try to see if there's some linear structure underneath, right? So the Friday before the break, we came up with the matrix of the operation of taking the transpose of a matrix, okay? Taking the transpose of a matrix is a linear transformation between finite dimensional spaces, and it has its own matrix, okay? And likewise, so this is what I think referred to by this self-referential structure of linear algebra. Linear algebra sort of handles its own problems and its own procedures, in a sense. Yes?
So at the beginning of that problem, we checked to see if they had non-zero determinants. If they have a zero determinant, can we not do this?
Well, it's not a basis then. It wouldn't work.
So then we just can't.
Yeah, then the universal diagram is off. You cannot use it. Because it's not a basis. You need to come up with a basis. Either you have a calculation error somewhere, or or maybe there's a typo or something like that. Yeah. Okay. Let's talk a little bit about signal processing then. We're going to spend tomorrow on signal processing. More specifically, it is digital signal processing. We can also do analog signal processing, but that is not sort of the more popular thing, I think, or it seems. And just as with computer graphics, I should just note that I don't know much about this area. I've been educating myself about it, but just take everything with a grain of salt. Yes.
What is a digital signal?
I'm getting there. A digital signal is nothing but a sequence of numbers. It's that simple. It doesn't really tell you much. But so, for instance, this recording that I'm taking is a digital signal, right? So we start with something like an analog signal. That's sort of like a continuous function. So we can think of, or rather, function whose inputs are just, it can be any number, single variable functions. So what we denoted in this class by this is, in the context of signal processing, is called the space of continuous time signals. So you start with, there's a flow chart for this. So you start with an external signal, let's say. Okay? You're speaking or something, and then the camera is recording. And you first put it through. This is one of the pipelines, one of the common pipelines in digital signal processing. So first you go through this item, this filter called a low-pass filter. Okay? Initially, your signal looks like this. So it has a graph like this. So you start with this, but then it has a bunch of like oscillations, small oscillations. This is something like a noise or something. What the low-pass filter does is that it smooths out this curve. Okay? So at the end of this, you still have, ups and downs, but it's not as oscillatory. Okay? Let's imagine that this is the same thing as this, but with less oscillations. Then you go into what is called SNH. And this stands for sample and hold. So this is continuous time. Now you turn it into discrete time. So now this continuous picture turns into this. You sample the values at certain times, and you hold for a certain period, unit period. And so you get this sort of like a bar diagram, if you want. The point is that this is discrete, in a sense. Okay? And then you go through analog to digital converter, which now actually gives you zeros and ones. Okay? This is something like pre-processing. In a sense, signal processing seems to, some people say that it hasn't started yet. Now, in between, you have a digital signal processing task. Say, for instance, you have this message, you have this voice recording, let's say, and you want to send it through the internet. And like you coded everything into zeros and ones, and now you want to send it. What you want to do here is to compress it or make it, easy for error detection and stuff. Or you want to enhance certain properties of it, let's say. Whatever. We're going to see certain examples of this. You do whatever you need to do, and then you send the message, let's say. It's again zeros and ones and so on. And then you do everything in reverse order. Now we have a DAC. Digital to analog converter. Now you're back to this. And then you again go through a low-pass filter to get rid of all the side effects of whatever filter that you were using, whatever signal processing paradigm or algorithm you were using. It has certain side effects. You want to get rid of those before giving it to the user. And so you go through, again, a low-pass filter, and then you have the output signal. Okay? You don't need to know the names of this. Obviously, this is a whole field in typically electrical engineering, as far as I understand. But I just wanted to mention some of the things. Now, specifically, these type of things, low-pass filters, or more generally, linear time invariant filters, turn out to be very important in this field. And so tomorrow we're going to discuss specific examples of signals. We're not going to go this much into detail. We're just going to look at some examples of signals and some linear time invariant filters. But we're not really going to discuss this low-pass filter because it is somewhat more complicated to discuss. Okay? Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to spend some more time on digital signal processing. Here's a basic definition I wanted to give. The definition: a signal, a digital signal, discrete digital signal, is a bi-infinite sequence of real numbers. It's as simple as that. And the space of signals, it's a vector space of infinite dimensions that I'm going to denote by this approximation to Blackboard S. So it's like two S's. It's just a space of all those functions, right? A sequence is just a function indexed whose arguments are integers. The point is that it goes to positive infinity and negative infinity. So it is bi-infinite. That's what I mean by bi-infinite. So this Z is integers. And when we first talked about a couple of examples of vector spaces that are very important, one thing that I mentioned was that given any field, there's a specific vector space that seems to be important, and more often than that, there's a specific linear transformation that is important. And in the context of digital signal processing, it's the shift operator. I'm denoting this by rho because it's right shift, and it's a linear transformation from the space of signals to itself, and it takes a signal x, produces y, and how are these x and y related? In pretty much the same way as in the case of shift operators for continuous time signals that we discussed the other time, last week, or the week before, I guess. So the output is going to be x of n, but with a minus 1 inside the argument. So you're shifting the signal by 1. So here are a couple of examples that are very important. Let's just look at some important signals. The first important signal, I would say, is the unit impulse signal. In the book, they just call it delta, but I think it's better to call it unit impulse. Another name for it is what is called Dirac delta. So this signal, okay, so this should be a sequence of real numbers. So delta of n, okay, I need to tell you what delta of n is 1 if your index n is 0 and it's otherwise 0. So if n is not equal to 0. Now, this is sort of this formal definition, but it's also good to think about how to visualize signals. And one way you can do this, there are two very common ways. One way is the engineering way, I would say. Okay, so this is your signal, so this is your graph, and let's say that this is time 0. So this index of the sequence, I want to think of as time. Okay, so this is time 0. This is my time 0. At time 0, my signal is at 1. Otherwise, it's at 0. Okay. So this is one way of drawing. If you want, you can sort of put bars, say in the context of stocks and stuff. We're talking about sort of, for instance, this camera recording and everything, but at the same time, something like the stock exchange, or stock exchange is also, you can think of as signals. So this is one way of representing. This is graphical. Another way of representing signals is by using the so-called ticker tape representations. So I'm just going to pretty much do the same thing. I'm just going to draw sort of like a ticker tape, and I'm going to put numbers according to what I should see. And just so that it is clear what is time 0, because when I just draw it, it's not clear what is time 0, I want to put 2 bars at the box that represents time 0. Okay, so according to the ticker tape representation, then this is this. So this is graphical representation of a digital signal. And this is the ticker tape representation. So as I understand, back in the day, back in the times when stocks were like they were physical objects, let's say, in the sense that they weren't digitized, each stock had this ticker tape, and each unit time, its cost was being printed out. So think of it that way. That's why it's called a ticker tape. There was like a machine here, and it was producing the value, let's say, monetary value of the stock. So these are, both alternative ways of representing the same thing. Here's another example. This is also very important. Unit impulse was the first example. The second example is unit step. And so this is defined like this. U of n is 1 if n is non-zero and 0 otherwise. And again, graphical representation against ticker tape representation tells you this. Let's say that this is times 0. So here, this should be like this. And in the ticker tape representation, it should be like this. Okay? Any questions so far? So this is a signal that turns on exactly at time 0 and then it turns off. This is a signal that turns on exactly at time 0 and it stays on. Okay? Another example. Constant alternating. Yeah, this is sort of important. Another example is a family of signals. These are exponential signals. And so, for instance, let's consider this. E of n, let's say, powers of 2, let's say. So it's going to be 2 to the n. Okay? So let me try to be a little bit more clear. So this is my time 0. Of course, when n is equal to 0, this has to be 1. So this is 1 over here. And as n increases, as you go into the future, let's say, this grows exponentially. So at time 1, it is at 2, then it's at 4, and so on. And then when you go in negative time, it's going to be at 1 over 2, 1 over 4, and so on. So if I wanted to write it here, I would write it like this. 1, 2, 4, 8, 16, and so on. Well, 1 over 2, 1 over 4, 1 over 8, 1 over 16, 1 over 32, and so on in this way. Okay? There are a couple more. Of course, this is not the end. These are important examples of signals. So now let's figure out how this shift operator operates. let's use the Dirac delta. So this is going to be a new signal, okay? So it's a function at the end of the day whose arguments are integers. And so based on this, I can just write down this expression at n. So that's rho, so right shift of the delta signal at time n, according to that formula over there, is equal to delta of n minus 1. Okay? Now, delta of whatever, we know what it is, and so I can just write it like this. So it's either 1 or 0, depending on the argument. Now, there, when we wrote this definition, the input was n, and that's why I saw n here. But there, the input is n minus 1. If you want, you can think of n minus 1 equals m, and do things that way. In any event, instead of n over there, I should be writing n minus 1. And again, I can simplify this a little bit. It's 1 if n is equal to 1. It's 0 if n is not equal to 1. So this is the right shift of Dirac delta. Graphically, we can draw it like this. So this is time 0, 1, 2, 3, minus 1, minus 2. And using the ticker tape, we have this. So you see, this is time 0. So here I should put 0. Here I should put 1 and 0. Okay? Now, this ticker tape notation is useful when you're trying to handle this shift operator. Because here's what I can do, for instance. Instead of having one ticker tape, I can have 2 ticker tapes and compare the 2 signals, if I want, very easily. So let's say that here I'm going to put delta, here I'm going to put rho of delta, and let's say I can put rho inverse of delta above. It's, of course, an invertible transformation. So I have three ticker tapes, and I want to synchronize their times. Okay? So for each 3 signals, this is the time 0 value, and then time 1, time 2, and so on. Okay? Now delta is like this: 1, 0, 0, 0, 0, 0, 0, and so on. Maybe I shouldn't draw this. According to what we discussed above, rho of delta should be so that this is 0 and this is 1. Any guesses as to how I should fill this up? Rho inverse of delta. So it should be an operation that does the exact opposite of what rho does.
Would it be a 1 to the left of delta?
Exactly. So rho is right shift, that's why it's rho, and there's the inverse of it is left shift. Okay? And the idea is that in the ticker tape symbols, in the ticker tape notation, applying this shift operator rho corresponds to taking your ticker tape, moving it this way by 1 unit. And of course, applying rho inverse corresponds to moving to the left. Maybe I should write it again. So if you have an arbitrary signal, let's call it x, and if you apply rho to it, this is what happens. Again, I want to synchronize the signals. So I'm starting like this. X of 0, right? The value of the signal x at time 0, x of 1, x of 2, and so on. And here it is x of minus 1, x of minus 2, x of minus 3, and so on. Now, in the second ticker tape, I should see rho of x. And based on what we discussed here, this is the effect of applying rho. Okay, which means that I should see here x of 0, here x of 1, and so on, and here x of minus 1, x of minus 2, x of minus 3, x of minus 4, and so on. Okay? Any questions about these so far? This is not something completely new. We already had seen something like this in the context of this function space f. It's just that the interpretation is a little different, I think, quite possibly. Here, in the context of digital processing, you really want to think of this as, so this horizontal axis as your time. So now, one important concept in this area of digital signal processing is what is called filters. And a filter is nothing but a transformation. They just use the word filter for transformation. It takes a signal, gives you back another signal. So that's a function, transformation. A filter is a transformation, is a function. A function, let me use capital F, from the signal space to itself. But of course, this class is a linear algebra class. So we really want to look at linear filters. What is a linear filter? It's a linear transformation. Let's call it T. Okay. Now, what do I mean by linear transformation here? Well, I mean that it satisfies the axioms of being a linear transformation. And you add, or maybe we should do an example of adding some signals. Let's do that, in fact. So, for instance, let's consider this. The way you add and scalar multiply signals here is the same way you would do with functions. They are functions, and this is a function space. We just add values corresponding to the same times. So let's say that I have a signal that sort of ramps up starting from time 0 and then goes down. Something like this. So let's say that I'm just going to draw the ticker tape. And so that's going to be the definition. So for negative time, it is 0, let's say. Explicit here. And starting at time 0, let's say it's at 0 here, and then 1, 2, 3, 2, 1, 0, and then 0 afterwards. So that's my x. What we can do is this. Let's take another one, y, and the second row is going to be for y. Well, let's say that y does the same thing, but for this side. So 1, 2, 2, 1, let's say, somewhat different. And otherwise it is 0. And surely if I were to add these up, I would get this ticker tape. So all I need to do is to add the corresponding entries, right? 0, 1, 2, 2, 1, 1, 2, 3, 2, 1, 0. Okay, this is how you add. And if you wanted to scalar multiply, let me put above c times x, or let's say 2 times x. What is important, again, is that you're keeping track of your times. You don't mess up the times. So if I scalar multiply this row by a factor of 2, I have this. 2, 4, 6, 4, 2, 0. Okay? Another thing you can do is you can take a signal, something like x, and you can rewrite it in terms of deltas as a linear combination of shifts of deltas. Here's what I mean by that. Again, taking this x signal, so I have 1, 2, 3, 4, 5 non-zero entries. So I can do something like this. Let me write it somewhere else. So this was, okay, like this. And I want to split it into 5 shifted Diracs. So 1, 2, 3, 4, 5, then synchronize. I don't need to. So this signal is like this: 0, 0, 0, 0 at time 0. I'm just copying this row. 1, 2, 3, 2, 1. 3, 2, 1. Then let me add one more here. 0. And it goes on like this. So let me take this signal, 1. And then this signal, 2 here. So you see what I'm doing is I'm splitting my original signal into signals that are non-trivial, that are non-zero, only at a single time. And then 3, 2, 1. And everything else is going to be 0. So now, for instance, this first piece, so what this whole thing represents is that if you were to take all of these, all five of these ticker tapes, add them up, you get back the original signal. Now this is nothing but rho of delta. Okay, that's the one over there. How about this? How can I represent it using the shift and delta?
I'm sorry, how come you say the second row is rho of delta?
Because of this.
Oh,
Yeah, I shifted, so delta has 1 only at time 0.
so you want to like have a transformation that describes each row, is what you're asking?
I want to have a name that possibly uses rho and possibly uses delta that represents each of these signals.
Could you do, for the second row, could you do 2 rho of delta plus 1 or something?
Okay, if you apply rho once, you move to the right once. Now you need to move to the right 2 times.
So 2 rho of delta.
Rho squared. Yeah,
Rho
yeah, 2 rho squared of delta. Apply shift 2 times, and then scale by a factor of 2.
and then it would just be like, you know, n rho n of delta.
Exactly. Yeah.
Or maybe not, because it goes.
Yeah. Yeah. You got the idea. And so this is going to be 2 times rho to the 4, so 4 shifts of delta, and then finally rho to the 5 of delta. To sum up, we have that x is a linear combination of shifts of delta. Let me write it above. So x equals rho of delta plus 2 times rho squared of delta plus 3 times rho cubed of delta plus 2 times rho to the 4 of delta plus rho to the 5 of delta. I wrote my signal x as a linear combination of shifts, right shifts, of the unit impulse signal. Is in the span of shifts of unit impulse. Okay. Now, let me ask you this. If I were to take a bunch of shifts of delta, and would these shifts, or shifted signals, would they be linearly independent? Now that we have a vector space, we can certainly talk about whether or not signals are linearly independent or not.
You just have a bunch of arbitrary shifts?
Yeah, I'm just taking, let's say, the second shift and then the 15th shift and so on. I'm just, I'm asking, are these signals linearly independent?
I would think not necessarily.
They can be made up of. Wait, so you're asking, which ones are you asking? Are you asking if each of the individuals that make up X are linearly independent?
We can work with that. Yeah.
In that case, I would say yes,
Why would you say so?
because they each essentially affect a different dimension, where the dimension would be the ticker position.
Yes, exactly. Yeah. So that's the idea. So you can think of these as like infinite dimensional vectors as well. Infinite tuples, if you want. And so for instance, the first shift has a non-zero entry only here. And no other shift of delta has a non-zero entry here. Okay? So here's a statement. Let me just do an example. Shifts of delta are linearly independent. I guess this is a statement, and the example for that is, let's say I take delta and 3 times delta, 3 row cubed delta. So how do we do this? I say a constant multiple of delta plus another constant multiple of delta to the 5 equals 0. This is what I assume. And I want to get that a and b have to be 0 numbers. Okay, this is what I want. Now, what does this mean? This is a signal. It's a linear combination of signals. Consequently, it's a signal. This too is a signal. It's the 0 vector. Okay, it's a 0 vector in the space of signals. 0 signal. So what this tells in terms of ticker tapes is this. So here I'm going to put delta, here row to the 5 of delta, here a delta plus b row to the 5 of delta, and for the last row let's just use 0. Okay, synchronize. Okay, delta is 1 only here. 0. And put a negative time also. Row to the 5 of delta is this thing shifted 5 times to the right. So 1, 2, 3, 4, 5. That's a 1. Everything else is 0. Now, if I were to add these two up with the corresponding numbers, now I have an a here and a b here, and everything else is 0. And of course, a 0 signal is that signal whose entries are always 0. But if this is the case, right, that's the assumption that you need to make to verify linear independence, then it must be the case that the entries match. So this has to match, this has to match. Okay? Does this make sense? And of course, there's nothing specific about, never shifting and then shifting 5 times. As long as you're shifting distinct units, you'll always get linearly independent signals, just using delta. Okay? So now you see I can start talking about linear subspaces of the space of signals. Now, this just says that this specific signal x is in the 5-dimensional space whose basis is these shifted versions of delta. Okay? Now, talking about the basis of the space of signals is somewhat iffy because it's an infinite dimensional space, and even though it is true that you can still talk about bases of infinite dimensional spaces, we don't do that in this class. It's slightly more abstract. We would need to discuss more stuff. But still, we can talk about finite dimensional subspaces of the space of signals. Now, one specific linear subspace of the space of signals is the space of finitely supported signals. In the book, this is denoted by S sub f. Let me just write it here. I'm going to continue from there in a second. Just want to give that definition. Yeah. So here's the definition. S sub f is the linear subspace of S that consists of finitely supported signals. Now, what does this mean? This means that any signal here is 0 beyond a certain time in positive time and beyond a certain time in negative time. So S sub f, by definition, is the set of, or the space of x's in S, such that there is an integer n, positive integer, such that after that, in positive or negative time, your signal is 0. Such that if n is larger than n, capital N, in absolute value, then x of n is 0. So this is like a finite time signal. Okay. Of course, this is more realistic to talk about, but it turns out that mathematically this is slightly harder to handle. There are certain benefits of using this in certain situations and using the general signal space in some other situations. Now, let me also say that by taking linear combinations of shifts of delta, I will always get a new dimension, just as in the case of the function space. And all of these, any linear combination of shifted deltas is going to be here. Okay? Because linear combinations are finitely many always. And if I'm taking finitely many shifts of Dirac, that means that I'm only doing things in finitely many coordinates, which means that beyond a certain time, my signal is going to be 0. So let me write it here. Any linear combination of shifts of delta is in S sub f. And in fact, let me also leave this as an exercise. This is slightly perhaps too abstract for this class, but it's a good exercise if you want to think about this. S sub f as a vector space is isomorphic to the space of polynomials. Okay? So you see, you can think of these signals as signals, ticker tapes, whatever, but you can also think of them as polynomials. So for instance, this isomorphism, one of the isomorphisms that you can write, would say that that x above is, let me do it here. So this, one way to do this is to note that if you were to take x, and if you say, oh, this is nothing but an abbreviation of the polynomial, okay, so 0, 1, 2, 3, 4, plus t to the 5. Yeah, this row is nothing but an abbreviation of this particular polynomial. Certainly it's an abbreviation. And in terms of linear algebra, the way you add and scalar multiply signals is exactly the same way that you would add and scalar multiply polynomials. Yeah, okay. There's a trick here, but I'll leave that to you if you look into that. Any questions about anything here so far? Yes.
On the middle one, the S of, that thing, is it the absolute value of little n?
Oh, yeah. Yes, absolute value. Yeah, so what I mean here is that any signal in S sub f should be so that when you, let's say, draw the graph of it, this is time 0. So there's this box of finite length, here length is n, such that within it anything can happen, but outside of it, it's always going to be 0. The point that the reason why this is slightly cumbersome to use is that this integer is not uniform. So given any signal, the integer may change. So the box shifts around, and that makes things a little hard to write down, perhaps. But certainly this is more realistic. When you're trying to do actual signal processing, your signals are going to be finite. Eventually, your voice, or even if it's not necessarily finite, it's still good to think of them as finite, because there's always, for instance, noise. Even when I'm not talking, the microphone is recording things. Yeah.
So if anything can happen within the box, can it be 0 within the box?
Yes, it can be 0 as well. Well, it has to be a vector space, so it has to have a zero signal. Yeah.
And then what is like a supported signal from like the original definition?
Finitely supported. So this box is the support, is the term of art.
So it's just a space that has those signals in it?
Well, let me just state this. So it is this, finitely supported. And this box for any given signal is what you call the support of the signal. Okay. So this is not, the support is not part of the space of signals. It's a part of the graph.
Okay.
Right, so
it's just a space on the graph that the
yes.
signals can be in?
Yes. Yes. So these are, for instance, finitely supported. The support of this is this. Okay. Yeah. So so it's
like your set of numbers, basically.
it's my set of entries where there's a non-zero number.
Okay.
Yeah. Okay. Yeah.
So when you say that, this space of functions, S sub f,
Yes.
is isomorphic to the space of polynomials.
Yes.
When I was looking at that chart, it made sense to me to say that it's like isomorphic to the unit vectors, where the dimension of the unit vectors is just equal to however many dimensions, like S sub f has, or whatever one you're dealing with. When you say that it's isomorphic, are you saying like if you wanted to, like you could do a change of basis to the polynomials and deal
Essentially.
just in the polynomials?
Yes. Yeah, so this isomorphism literally means that I can take this signal and I can interpret it as this polynomial.
Well, actually, so I said change of basis, but change of basis doesn't mean that you're like going from one space to
Exactly,
another space.
yeah.
It means that you're just changing like the building blocks within the same space.
Yes. So the space changes here, but that's where this issue of like type and token comes into play. Like, are these like the same thing or different, or how they're different and
It's
everything?
like I want them to be the same thing.
Yeah.
But I guess like it's not by the definition explicit.
I think what it is that the psychological access that you have to these objects are distinct. These are psychologically distinct objects, I would say. Like the polynomial, I have a different understanding of a polynomial compared to a signal. They are the same underneath the hood from the perspective of linear algebra. But I think they have some distinctions. So certainly you wouldn't be able to convince engineers by saying, this is nothing but spaces of polynomials. Just use polynomials. They're not going to do that. Okay, because the way people call things and the way people represent things or think about things somehow, I think, is subordinated to the problem that they're trying to solve. So.
It seems like finding isomorphisms is pretty hard.
Well, at first it seems like it, but eventually you start seeing patterns. Let me put it this way. So the first thing is, of course, that under isomorphisms, the dimensions are going to be preserved. So that would be sort of like the first heuristic. In this case, they're both infinite. It turns out that they're the same type of infinite, so that's not an issue. But certainly, this is not a finite dimensional space. It's never going to be isomorphic to a finite dimensional space. Okay, because you have, yeah, because you can just keep shifting Dirac and get a new dimension. Yeah.
So, but like, I guess when you say like it's isomorphic, it like breaks down. Like you couldn't, because if you have a polynomial, you can like plug in some parameter and then
Yes.
you get like a number, but that doesn't really make sense.
Yeah, so you see, yeah, so this idea of plugging in t equals 15 makes sense here. It has no sense here. That's not it is in a sense a linear algebraic operation, but
It just doesn't make sense.
yeah, not at least immediately.
So in this case, does t equal p of delta?
Say again?
So like for this one, since like that's the same equation we wrote earlier just before it had deltas in it.
Oh, yeah, no. So
Is t just equal to p of delta?
it's not quite equal. What I'm saying is that this signal x, okay, I can interpret this signal as this specific polynomial. This was just a comment for this particular exercise. This is how you would write down the isomorphism. You would need a linear transformation from the space of signals, right? So you need to tell me how you associate to each signal a polynomial and vice versa. And you need to do this in a linear fashion.
So
Okay.
is the blue an isomorphism?
No, it's just a hint as to how you could write that isomorphism. Yeah.
And so I guess like when you're able to say something like thus the signal x is in the span of shifts of unit impulse, like part of what that means is that given some arbitrary signal, you can ask the question, can I make this signal out of unit impulses?
Yes.
Like hypothetically, if you had a device that could.
Yes, exactly.
You know what I'm saying?
Can you handle your signal one at a time?
Okay.
That's the idea.
Okay.
Yeah. I'm running out of time. I want to give one more definition. This is also very important. Filters are functions from the space of signals to itself. Linear filter is a linear transformation from the space of signals to itself. But what is perhaps more useful is LTI filters. LTI or LSI filters L stands for linear, T stands for time, S stands for shift. They are the same thing basically. I stands for invariant. Linear time invariant filter. So this is a linear transformation, T, that commutes with shift. T such that the bracket of T with rho is 0. Okay, so this means that T rho x is the same thing as rho Tx. So this is a filter, right? Like it takes signals, gives you back some other signals, and somehow it is defined in such a way that it doesn't matter where you're trying to, so which slot you're looking. It's always given by the same rule. That's the idea. So one example for this, which is useful, is a moving average. Okay, you can take a signal and you can look at its moving average. Let's say between 0 and 1. So you take a small box I'm running out of time, so I'm not going to go too much into detail. Filters are LTI. Let me say another thing. This you may hear low pass filters and high pass filters, or band filters, or band pass filters are LTI. High band pass filters are LTI also. Unfortunately, we won't be able to go too much into details about even what these are, because in order for these filters to make sense, we need to develop Z-transforms and stuff, and obviously we don't have time for that. But in any event, this is just a taste of digital signal processing, some basic definitions. Probably in the next problem set, you're going to see some exercises around these things. And that covers all about the second midterm. Tomorrow, we're going to have a review, come with problems. And on Friday, we're going to have our midterm in class as usual. And that's it. Thank you. See you later.